Okay, it's the first use of a balanced equation for a chemical reaction. Will remind us with one type of calculation that we learned previously, which is the empirical formula calculation. As we said at the time, empirical formulas are experimentally measured in combustion analysis, in which you burn your sample with oxygen, which is gonna convert all the carbon into carbon dioxide, all the hydrogen into water. And then you absorb water in one compartment and weigh it, and then absorb carbon dioxide and weigh it. And from the grams of each one of these substances, you can find the number of moles of carbon and hydrogen in your compound. And from the number of moles, you can find the empirical formula as we learned previously. But in general, how to read chemical reaction or what type of information you extract from chemical reaction, it basically the balancing coefficients, which are the numbers in front of each substance, gives the ratio of moles of each of these substances to each other. So it says here that the reaction proceeds with a ratio of 2 atoms of magnesium to 1 molecule of oxygen to make 2 formula units of magnesium oxide, or 2 moles of magnesium reacting with 1 mole of oxygen to make 2 moles of magnesium oxide. But it's not grams to grams to grams. It's moles to moles to moles ratio, which means it's going to allow us to only interconvert between the number of moles of each species in the reaction, interconvert between number of moles of reactants and moles of products or moles of reactants to each other. So it's in a sense is similar to the composition stoichiometry that we learned before, where the ratio in the empirical formula of a compound allows you to convert between the moles of the whole compound and the moles of one of the elements in that compound. Basically, here it says that each 1 mole of water contains 2 moles of hydrogen. So you can use this ratio as a conversion factor to convert from moles of water to moles of hydrogen and vice versa. Similarly, for balanced reaction coefficients in this reaction right here, you will get a ratio between the number of moles of each species. These ratios are also conversion factors that can be used to convert between number of moles of each substance. So the ratio between moles hydrogen and moles oxygen is 2 to 1. This should allow us to convert between number of moles of hydrogen and number of moles of oxygen in our reaction and vice versa. Ratio between moles of hydrogen and water is 2 to 2, which is basically 1 to 1. And again, that is going to allow us to interconvert between number of moles of hydrogen and the number of moles of water that would form in this reaction. So if you have 6.5 moles of magnesium completely reacting with oxygen, how many moles of oxygen is going to be required? So to carry out this calculation, you start with writing the equation that describes a reaction. It says reacting magnesium with oxygen to make magnesium oxide. Second step is going to be balancing the equation. You have to make sure that the number of atoms of each element is the same on both sides. Oxygen is 2 here, but 1 here, which means we have to put 2 as a coefficient in front of magnesium oxide, and that will make magnesium 2, which means we have to put 2 in front of magnesium on the left-hand side. Now, this is a balanced equation that gives us the correct stoichiometric equivalence between each species in the reaction. 2 moles of magnesium is equivalent to 1 mole of oxygen, or 2 moles of magnesium is equivalent to 2 moles of magnesium oxide. 1 mole of oxygen is equivalent to 2 moles of magnesium oxide. Equivalent means that it will completely react with that amount of the other substance. These chemical equivalent ratios can be used as conversion factors to interconvert between the number of moles of each species and the others. So to answer this question, we have moles of magnesium and we want to find out the equivalent moles of oxygen that would react with it. So we start with 6.5 moles of magnesium, and then we need a conversion factor from the balanced coefficient equivalencies that converts moles of magnesium to moles of oxygen, which is this one right here, which says that 2 moles of magnesium is equivalent to 1 mole of oxygen. Now we carry out the calculation, we see that moles of magnesium will cancel out with moles of magnesium, and you will get the number of moles of equivalent oxygen that would react when this reaction is complete, which is going to be 3.25 moles oxygen. And of course, you could do a similar calculation to find the equivalent amount of magnesium oxide that would form. So 6.5 moles of magnesium. If reacted completely, it would have formed from the equation here. The ratio is moles magnesium in equivalent to moles magnesium oxide is 2 to 2 or 1 to 1. It's basically the same thing. So if all of that number of moles of magnesium would have reacted, it would have formed the same number of moles of magnesium oxide. If we have a combustion of methane, which is basically the reaction of burning methane using oxygen to form carbon dioxide and water. So if we start with 6.75 moles of methane, how many moles of oxygen are needed for a complete reaction of that amount of methane? First step is going to be writing the balanced equation to set up the mole to mole ratio between methane and oxygen. So methane is CH4. It's going to react with oxygen, which is O2, to form carbon dioxide plus water. This is not a balanced equation yet. It just summarized the species that will participate in the reaction. But we have to make sure that the number of atoms of each element are equal on both sides. Balancing the equation is our first step. If we start with carbon, it's already balanced. So we can move to hydrogen. We have 4 hydrogen here, but only 2 here, which means we need to multiply it times 2, or we need to add 2 as a coefficient in front of water. Now we have hydrogen atoms balanced in the equation. We move to oxygen. Oxygen is 2 here and 2 here. But we only have 2 oxygens on the left-hand side, which means we need to multiply it times 2. So it's going to be 2 oxygen molecules. Now we have 4 oxygens on the right-hand side and 4 oxygens on the left-hand side. Carbon is already balanced, as we said. So that's a balanced equation for the reaction. Let's erase these workout coefficients to clean up and continue to the next step. From this balanced equation, we have equivalencies or more ratios between each species and the others. It says that 1 mole of methane is going to react with 2 moles of oxygen. So the mole ratio between methane and oxygen is 1 mole methane to 2 moles oxygen. The mole ratio between methane and carbon dioxide is 1 mole methane to 1 mole of carbon dioxide. Ratio between methane and water is 1 mole methane would produce 2 moles of water if this reaction is complete. These are 3 mole to mole ratios that we got from the balance equation that should allow us to convert between the number of moles of methane and the number of moles of any other species in the reaction: oxygen, carbon dioxide, or water. It's asking here to calculate moles of oxygen that would be needed to completely react that number of moles of methane. So we start with the number of moles of methane and use the mole to mole ratio as a conversion factor. So we want the mole to mole ratio between methane and oxygen, which is right here. 1 mole of methane is equivalent to 2 moles of oxygen, which means that number of moles of methane would require twice as much moles of oxygen, which is going to be 13.5 moles oxygen. We can similarly calculate the number of moles of any other species, like the number of moles of carbon dioxide that would be produced, or the number of moles of water that will be produced when this reaction is complete.